Hello, welcome to our semiconductor education program. This is Vincent Chang. In this lecture, I'm going to present an interesting oscillator called active filter tuned oscillator. Active filter tuned oscillator. So here's the circuit. It seems a little bit complicated for a beginner if this is your first time, but let me try to break down several things before we go to the oscillators analysis. Okay. The first is the general impedance converter, an Antoniou inductance simulation, and then it's embedded with a bandpass filter, and then the clamping circuits. So three parts. Let's start with the Antoniou inductance simulation. And this circuit, the red highlight, is going to simulate an inductance. Okay? It's going to simulate an inductance. So what's the equivalent inductance? What's the equivalent inductance? It's going to be, you can put down this on your note. So C2, R1, 3, 5 divided by R4. Okay? So if you kind of forget, let's quickly review what we learned before. Antoniou general impedance converter. So starting with this, so two negative feedback loop, right? Two negative feedback loop. And then let's bring back the previous oscillator circuit and compare the red highlight within that circuit on the top left corner with this one, okay? So this one, the slide shows the general impedance. So we're starting from this. And through analysis, this is the result. Z1, 3, 5 in the numerator, and 2 and 4 in the denominator. So in the Antoniou inductance simulation, then Z4 now is replaced by a capacitor. So then the rest of the impedance is realized by a resistor. And then here's the outcome. The input impedance, the general impedance, the whole circuit is going to serve a two-terminal device, which equivalent impedance equals this, as equivalent inductance. And this equivalent inductance equals what? 2, 1, 3, 5 in the numerator divided by R4. So now let's keep this result and bring back to the original circuit. So let me ask you, what's the equivalent inductance for the red highlight? So you just plug in, replaced R1 with 4R, R3 with 3R, now R5 with R, and divided by 2R. And then the outcome, 6R squared C, like this. 6R squared C is the equivalent inductance. Right? So the first part is done. Antoniou inductance simulation. Let's move on to the second part. You see a bandpass, right? Now you see the inductance, equivalent inductance. So combining this inductance with its neighbor, the capacitor, and also the resistor, the series resistors QR, the lowercase q. And then these three guys generate a bandpass function, right? So this is the bandpass filter, the R and parallel combination of the L and the C. Let's quickly go through several important characteristics of this second order bandpass function. Number one, transfer function. Now here's the transfer function. And let's bring this into a standard second order bandpass filter function like this. So you can compare the coefficient, then you're going to get this, the pole frequency, the 1 over square root of L times C, and the quality factor, right? and quality factor. And then what's the meaning of omega 0? There are two meanings. So number one, it's the center frequency when you see the magnitude response. The center frequency of the bandpass. And then if you try to illustrate or analyze this by inspection, then there is only one condition, then the maximum transmission. The unity transmission will happen, which is the VO equals VI, which is the loop current equals 0. So when the loop current equals 0, the parallel impedance of the L and the C approaches infinite. So if you just put down this, because we taught this before, okay, let me just quickly go through. If you write down the parallel impedance of the L and the C, you will find out its denominator. And you let the denominator equals 0, then the associated frequency is called the resonant frequency. So the center frequency equals resonant frequency. Center frequency of the bandpass equals resonant frequency. So now, number 3. The 3 decibel bandwidth is the important figure of merit of the bandpass. The higher Q, the bandpass will become more selective. Higher Q, more selective. Omega 0 over Q is the 3 decibel bandwidth. Okay? So now, if we go back to the original circuit, the oscillator circuit, all right? So what's the quality factor of this bandpass? Or bandpass? You see a bandpass, right? The blue plus the red equals a bandpass. It's the bandpass filter. So what's the quality factor? So now we plug in the bandpass. This represents a bandpass input and output. The relationship between the bandpass input and the bandpass output is going to create this kind of magnitude response. So let's start with the center frequency. So center frequency is the 1 over square root of L and the C, because we have to replace the L with 6R squared C, right? So then it's going to be this. So the square root, the 1 over square root 6 times the RC is the center frequency of the bandpass embedded in this oscillator circuit. Number 2, quality factor. Quality factor. So we can't just put L. So L has to be substituted by the 6R squared C. So then it's going to be this. So interesting to see the quality factor of the bandpass is proportional to the constant factor of the resistor, okay, the lowercase q. So the higher lowercase q, the higher capital Q, which is the quality factor of the bandpass. So now let's keep this result. And then move on from the bandpass to the limiter. So the limiter, so you see the diode, cathode, anode. For the limiter, then let's try to just use a transfer characteristic. So don't get confused between the input and output. For the limiter, because signal comes in, signal comes in from the V out, right? Let's go to the limiter and then go to the V2. So the V2 is the limiter output. V out is the limiter's input. So we need to output versus input, the V out, V2, see? V2 versus V out. Of course, this is the ideal. It's kind of ideal in terms of with respect to the V out. Because in reality, there's going to be a dead band concerning the turn-on voltage of the dial. Okay? So let's try to simplify these matters and ignore the back end. Now, dead band. Ignore. So when the dead band can be ignored? If the V out is large enough. Okay? So then the dead band is can be neglected compared with the magnitude of the dead band. So if the dead band is neglected, then we can draw this. All right? So in short, when positive V out, positive constant output. For the positive, I'm talking about the V out, that means the input of the limiter, all right? So for the negative V out, negative limiter input, and then the constant negative output. So concerning this kind of symmetric with the opposite polarity constant output. So what kind of waveform V2 will generate? Square wave, right? Oh, before we mention about the square wave, let me just highlight one more thing, okay? So actually, this kind of circuit can be interpreted by this. It's a bandpass with a limiter, okay? So combining a bandpass and a limiter and put it in within what? A positive feedback loop. So see the positive non-inverting terminal of the left-hand side op amp. Excuse me. So non-inverting input of the left-hand side op amp. So it forms a positive feedback loop. So if you take a bandpass, in other words, if you take a bandpass and a limiter and put it within a positive feedback loop, it's going to create an oscillator, all right? So as I mentioned 1 minute earlier, I said concerning this limiter's transfer characteristic, the symmetric output but with the opposite polarities. So what kind of waveform V2 will create? A square wave, right? And then now you send a square wave. If this is a square wave, and you send a square wave into a bandpass, then the output of the bandpass is going to be messy, right? Why? Because if you ever learn the Fourier series in engineering mathematics, so you understand this. The so-called square wave is actually an addition, a summation of an infinite number of the sinusoidal wave. And the first sine wave is called the fundamental frequency component. And then the rest of the sine wave is called harmonics, right? So think about this. If you send those kind of square wave with the concept of Fourier series, the summation, the infinite summation of many, many sine waves, and you send this into a bandpass, the output is still messy. But if the Q is very high, let's assume it's a very high Q, which means what? Which means the bandpass is highly selective. Select whom? Select which frequency. So only the frequency component, the same as the fundamental frequency, the same as the center frequency, can get the maximum transmission. The rest of the harmonic will be attenuated greatly, right? In other words, the output of the bandpass under this highly selective bandpass assumption. So the output of the bandpass can be treated as a kind of beautiful or pure sinusoidal wave, all right? So this is why at point Vx, it's going to create a sine wave. But the point X is not a good output. Why? It's a high impedance output. What do we mean by the high impedance output? Which means the output voltage, the signal, is gonna highly affected by the external load. So we gotta find out a low impedance node. This is where the V out shows up, right? So then the real output of this sinusoidal wave is gonna be taken from the V out. But what's the relationship between V out and Vx? Vx equals V2, V2 equals V4, right? Because the two virtual short. And then V4 equals what? V out is the divider. The 2 plus 1 in the denominator and the 1 are in the numerator. So 1/3. So V out equals 3 times Vx. If you are not happy with this 3 times, that you can increase 2R, right? So you can just adjust the resistance value and create the multiplication between the V out and the Vx. But in this case, I just want to give you a concept. So it's the 3 times. So the red sine wave, which magnitude will be the 3 times of the blue sine wave. Here's the takeaway. So what's the center frequency? The center frequency of the bandpass will become the oscillation, the frequency of oscillation of this oscillator. So if the output is taken from a good output, a low impedance output, then it's going to serve a sinusoidal oscillator. So which frequency is going to be decided by the center frequency of the bandpass filter. And what's the key concept behind this? To make sure you can fully understand the operation of this, I think the keys lies on these two blocks, right? The bandpass block and also the limiter block. So when you see this, you need to just pop up this kind of concept and bring back to this. Okay? When you see this, so you simply just grab the magnitude response of the bandpass and also the transfer characteristic of the limiter circuit and bring this back. And bring this back. So the output, if take at the point V2, is a square wave. But through the bandpass, the filter function, under the assumption of the highly selective, higher Q, very large Q, then the VR is going to create a sinusoidal waveform, which amplitude can be adjusted by just tuning those resistance value, right? So I hope you enjoyed this lesson. Thanks for watching.